we will now learn the most powerful theorem that we will in our class, the fundamental theorem of algebra. Now before we do, let's look back on some things we've already learned. The first type of equation that we learned to solve were linear equations. Linear equations have degree 1, and we would always find one root. Next, we solved quadratic equations, which has degree 2. And we found that these always have two roots, as long as we count complex roots and multiplicities. And in the one example that we looked at of a polynomial with degree 3, we found 3 roots. This leads us to believe that a polynomial of degree n has n roots. The fundamental theorem of algebra says that a polynomial p of x with degree of p bigger than or equal to 1 has at least one real or complex root. A consequence of the fundamental theorem of algebra is that every polynomial of degree n has n roots. Well, why does having at least one root mean that there are n roots? To answer this question, let's look at our factoring theorem that says a polynomial p has root k, in other words p of k equals 0, if x minus k is a factor of p of x. So if we have a polynomial p of degree n, the fundamental theorem of algebra tells us we have a root. Let's call that root k1, and p of k1 is 0. Now the factoring theorem tells us that p of x equals x minus k1 times some other polynomial q of x. And what's the degree of q of x? Well, we saw that the degree of p has to be the degree of x minus k1, which is 1, plus the degree of q. So since the degree of p is n, and the degree of x minus k1 is 1, we get that the degree of q must be n minus 1. But now, again by the fundamental theorem of algebra, q must have a root. Let's call that one k2. And the factoring theorem tells us that q of x can be written as x minus k2 times some other polynomial, w of x. Now, we can rewrite our original polynomial p of x as p of x equals x minus k1 times q of x, which is x minus k2 times w of x, where the degree of w of x now is n minus 2. And we can continue this, rewriting w of x as x minus some other root k3 times t of x, which has degree 1 less again, n minus 3. And this continues n times until we get down to degree equals 0, because then the fundamental theorem of algebra doesn't give us a root. But that's because it's just a constant. And this constant a is going to be our lead coefficient, because if we multiplied this all out, our coefficient of x to the n would have to be a. So we can conclude that if the roots of p of x are k1, k2, k3, all the way up to kn, with lead coefficient a, that p of x can be written as a times x minus k1 times x minus k2 times x minus k3, all the way down the line for every single one of our roots until we get to x minus kn, our nth root. Notice that this is very similar to the factored form that we got for quadratics. The only difference is that with quadratics, we only had 2 roots, where here we have a degree n polynomial with n roots.